Jai Hind everyone. Today I am going to discuss this topic, turbulent flow, in unit number 4 of your subject fluid mechanics KC 303. Okay. Now we need to discuss what is turbulent flow actually, what is laminar flow, how it can be transited from laminar to turbulent flow. Then we are going to do the analysis, how we are going to do the velocity distribution and do the shear stress distribution. So all the kind of particular distributions we should know, and obviously for knowing that particular kind of velocity distribution, shear stress distributions, we need to understand the basics first. Okay, so simply what we know about laminar flow. Laminar flow is what? If particles in particular flowing fluid, if they travel in a defined stream flow, okay, if the particles do not cross the waves of each other, then we'll say that kind of flow will be your laminar one. Okay, so also we say that a flow to be a laminar, okay, two things must be into consideration, that the velocity should be very low, and also the viscosity of particular flowing fluid must be very high. So there are two certain conditions you need to satisfy for the particular kind of flow is to be laminar flow. Okay. Now there is another number, another dimensionless number, that is Reynolds number. We used to identify or categorize that particular flow is laminar or not. We use Reynolds number. See, it is not only the character of flow or the type of flow. It does not only depends upon viscosity, it also depends upon Reynolds number that was classified by Reynolds. Okay. So the Reynolds number is what? Rho Vd by mu. Here rho is your mass density, V is your velocity, D is diameter of pipe, the diameter in which particular fluid is flowing, okay, and mu is viscosity. Let us suppose this is your pipe, okay, the diameter is having small d, and the particular fluid is flowing is having a viscosity of mu and density of rho. So how you are going to write equation for Reynolds number is that will be equal to rho V d by mu, or you can write it as V d by kinematic viscosity. Okay. So when this particular number for any kind of flow, when it is less than 2000, okay, when it is less than 2000, what you will say? That the particular kind of flow is laminar one. Okay. When this Reynolds number becomes higher than 4000, okay, when this particular Reynolds number becomes higher than 4000, we say that now the flow will be converted completely from laminar to turbulent. Okay. So this will be your turbulent flow. Now the question arises, what in between 2000 to 4000 Reynolds number? Okay. The situation in between 2000 to 4000, we say that there is a transitional condition where there is a conversion from laminar to turbulent. Okay. So that flow will be called as your transitional flow. So simple. So here we can, in this way, we can categorize what is laminar, what is turbulent, and what is transitional flow in the basis of Reynolds number. Okay. Now when we talk about velocity distribution equation in laminar flow, what we know very well, and if the students who are watching this video, and if they do not know what is the velocity distribution for laminar flow, the equation states for that particular situation is u equal to 32 nu u bar L divided by D. So this equation represent velocity distribution in laminar flow. Okay. When we talk about the velocity distribution in graphical form, here you can see this is your pipe, okay, and here we are showing you the velocity variation with respect to in y direction. Okay, that means let us suppose in this particular graph, if I go in upward direction like this, okay, so y is 0 at this particular point. Here you can see velocity is also 0. What is the mean by this particular equation? That the lowest layer which is sticked to the pipe wall, that is having the velocity of 0, or you can say that is sticked to the pipe wall, that will ultimately will come as velocity as 0 at y equal to 0. And whenever you go to the center of the pipeline, okay, center of the pipeline, that means this y here will be equal to if r by 2, okay, oh sorry, if this is r, or you can say equal to d by 2, okay. So at the center of pipe, the v or velocity of flow will be maximum or will be equal to v max, okay. Now that is for your laminar flow. But when we go to the turbulent flow, okay, in turbulent flow, actually velocity variation with time is very much random. See in this graph, velocity versus time, here you can see the variations like this, okay, variations like this. So this is the actual condition in case of turbulent flow. But on the analysis part, okay, for doing the analysis, for doing the complex situation to if we want to convert any complex situation to turbulent flow, we want to convert in simple forms, we just take this velocity variations, we take the average, okay, the time average, that will be equal to your v bar, okay, here it is v bar, or you can say time average velocity in particular layer, okay. Now when we plot velocity distribution in case of turbulent flow, this kind of a picture you can get, okay. Here you can see that here is a straight line, okay. Now again is a almost a constant, almost achieved a constant velocity here in zone number 2, and again there is a straight line, okay. So we are going to discuss what is this zone number 1, zone number 2, zone number 3, okay. Here it is also written that zone number 2, almost constant velocity because of the collision between the particles. See, there is a turbulent flow, okay, particles are flowing from one layer to another layer, then another layer, then coming back to one layer. See, there in the turbulent zone, there are a lot of collisions between particles, okay, collisions between particles. So after a long term, collisions, after a certain time, the particles achieve almost a constant velocity, okay. So after that particular certain time, we can write velocity like it is shown in zone number 2, okay. So this is the reason why we have zone number 2, okay. Now talk about zone number 1 and zone number 3, where you can see the straight lines, okay. Now that straight lines are actually because the variation in the velocity exists because of friction and viscosity of fluid with pipe boundary. See, variation in velocity, that means a particular variation or great variation are there because the pipe boundary is having an adhesion, okay, or you can say the friction with the layer of water. Simple. Now because of that particular friction and also the inherent property of fluid, that is viscosity, so because of this two factors, we got this velocity variation as shown in zone number 1 and zone number 5, okay. Now we are going to the next topic is shear stress in turbulent flow, okay. Now we know very well how we can define the velocity, okay, how we can define velocity distribution, how we can plot it in case of laminar and in case of turbulent flow also, okay. Now we are going to talk about shear stress in turbulent flow. We know very well what is the shear stress in viscous flow. We have studied it in chapter 1 properties of fluid. What is that? Is that tau equal to mu du by dy, where this du by dy is variation in velocity. Okay, tau is what? Shear stress, simply. Now, any kind of turbulent flow which is viscous also, the particular fluid is viscous also. So there is one thing is certain, that there must be a viscous stress also. Okay. Now the next part of this particular shear stress is that rather than this viscous stress, there must be a turbulent shear stress also. Turbulence shear stress means, that means because of the collision in between the particles, among the particles, that must be a created shear stress due to turbulence also. Okay. So the total shear stress in turbulent flow must be equal to the addition of viscous shear stress and turbulent shear stress. Okay. So here you can see tau v plus tau t. Okay. Now how you are going to write tau v as mu1 du by dy, as we know from the formula above written here. Okay. And the next term, turbulent shear stress, that is given by the equation for turbulent shear stress here written is given by J. Boussinesq, the French mathematicians. Okay. He has formulated this particular formula by his certain derivation and experimentations. Okay. So what this term states, that a turbulent shear stress must be equal to eta dv bar by dy. Okay, where y is what? Time average velocity. Okay, at a distance y, where eta is what? Your eddy viscosity. Okay, this is your eddy viscosity. Okay. Now there is a another term introduced by Boussinesq, is epsilon. Epsilon is equal to eta by rho. Okay, epsilon, you can write it as epsilon, or you can write it as T, as mentioned in this line. This is your kinematic eddy viscosity. Okay. So epsilon here or T here is a kinematic eddy viscosity, and all the other terms are written here. Now you need to understand here that the particular eta, the term eta is actually depends upon, it is function of characteristics of flow. The more the flow is turbulent, the more the value of eta will be. Okay. If we say eta is 0, that means for our case the flow is laminar flow, okay, or viscous flow. Okay, the correct term will be viscous flow, not laminar flow. Now again going further, again parental, a scientist gave the theory of mixing length concept. Okay, mixing length concept in turbulent flow. On the basis of his theorem, he also gave a formula for turbulent shear stress. Okay. Now what he has introduced to us is parental length. What is parental length and what is velocity? According to his theory is, that states that the velocity fluctuation in any direction is related to mixing length in this way. Velocity fluctuation, there may be two velocity fluctuation will be in x direction and also in y direction. Okay. So let us suppose we are taking any direction, and the velocity fluctuation, we can write it as, okay, and write it as L dv bar by dy. Okay. Now going further, L is simply what? The term we have taken as parental mixing length, L. Okay. But the exact definition for this parental mixing length is what? Let us understand. Okay. If there are certain layers, okay, in turbulent flow. Let us suppose this is a particle, okay, this particle is jumping from here to here, from here to here, okay. So what we are taking the shortest distance between this two layer. Let us suppose this was the position number 1 and this was the final position of this particular particle, okay. Particle have moved from here to here and here to here. Now the shortest distance between, or you can say the transverse distance between position 1 and 2, that will be your mixing length, okay. But there is another certain situation or condition that need to be fulfilled, is that whenever that particular particle is transferring, okay, and get mixed at this particular layer, the momentum of this particular particle should be equal to momentum of this layer in x direction, okay. Or you can say in further easy words, that average distance perpendicular to the direction of flow, a small fluid mass which travel before its momentum is changed by the new environment, okay. Now the shear turbulent shear stress equation given by parental, okay, is given by this equation, tau bar, or you can say tau itself, tau equal to rho L square dv bar by dy whole square, okay. Here dv by dy is your dv bar by dy is velocity variation, okay. Rho is your mass density and L is your parental mixing length, okay. So what will be your total shear stress? Again here in case of addition of, this will be your addition of viscous shear stress plus turbulent shear stress, okay. This is clear. So now we know what will be the expression for turbulent shear stress by the theory of parental, okay. Now talk about head loss. What are the head loss in case of turbulent flow? That is FLV square by 2 GD. This is your, the equation is called as Darcy's Weisbach equation, okay, where F is your friction factor, L is your length of pipe, V is velocity, and D is your diameter of pipe, okay. So whenever you are going to calculate head loss in particular flow in turbulent zone, okay, you can apply this formula for head loss, okay. Now the next topic is here, simply we need to differentiate what is rough pipe and what is smooth pipe, okay. In normal term, okay, in any situation, when we talk smooth pipe and rough pipe, okay, what we say, that if particular pipe is having a surface which is smooth, will be a smooth pipe. If it looks like rough, that we will say that it is a rough pipe, simple. But when we technically define it in our fluid mechanics, okay, how we can define it? On the basis of laminar sublayer. What is laminar sublayer? Laminar sublayer is a zone where we consider that the flow properties will be equal to the properties of a laminar flow, okay. Let us suppose an example here, okay. Let us suppose this is a pipe, okay, and I have taken this you can see the variations is actually the roughness, okay, or you can say uniform sand grain roughness. Just take the average height of all this roughness, you will get a line. Here you can see this line, the height of this particular line is k, okay. Now let us suppose we are also assuming the height of laminar sublayer, okay. Let us suppose the height of laminar sublayer, okay, or value of laminar sublayer is greater than this roughness height, okay. So what we will say, that this kind of pipe is your smooth pipe, okay. If it doesn't see, if the laminar sublayer here, laminar sublayer del dash is greater than k, so we are saying that pipe is smooth. if del dash becomes less than K, what will say? The pipe is rough pipe. Okay. Now, so here in this case where del naught was greater than K, you will say this is smooth pipe, or you can say this is smooth boundary. Okay. Now K is the equivalent uniform sand grain roughness. Here the opposite situation also, here you can see that the roughness height, the average roughness height is greater than this laminar sublayer. Okay. So we'll say that it is simple your rough pipe. Or by there are some expressions given by some experimental investigations, is that if K by del bar, or you can say del dash, is less than 0.25, this is your smooth boundary, this will be your smooth boundary. If it is greater than 6, then it will be your rough boundary. If it is in between 0.25 to 6, now the boundary is in transition. Okay. Now talk about the velocity distribution in turbulent flow in pipe. Now we are going to talk about the velocity distribution in turbulent flow in pipe. Here you can see that L is proportional to Y. See, when we are going to talk about the velocity distribution, the first thing parental assumed, or parental said, that the mixing length is actually proportional to the distance from the pipe wall. Okay, let us suppose this was a pipe and you are going upward direction, okay, at a distance Y, that Y must be in proportional with L. Okay. So here when you further solve it, you can get as L equal to kappa Y. Kappa is your Kármán constant, okay. So here Kármán constant or Kármán universal constant. Here is another equation for mixing length as 0.4 Y minus 0.44 Y square by R. But if you assume for a very close boundary, okay, or layer for a very close boundary, we can neglect this term. So what you are going to get as L equal to 0.4 Y. Okay, that means L equal to 0.4 Y, or you can get value for kappa or Kármán universal constant as 0.4. Okay. Now for Y to be very small, okay, L is simply what? Your 0.4 Y, as we have just assumed. So your kappa will be equal to 0.4. Now put the equation for turbulent shear stress given by parental. The equation is written as like this. Here L you can write it as kappa Y. So just put L equal to kappa Y in this equation, you will get it as equation like this. Okay. Now the shear stress also varies linearly with the radius. Linearly with the radius, that means what? Here you can see that wall shear is your tau naught. At some distance below, you are getting a stress or less stress as tau, and at the center of the particular pipe, you are getting shear stress as 0. Okay. Now again, when you move towards pipe wall, again the shear stress increases in linear direction. Okay. Here you can see the capital R is radius of this pipe. Small r is what? Small r is what? We have just taken at a distance small r from the center of the pipe. Okay. And here you are getting as tau, shear stress as tau. Just take the linear stress. You can write the formula as tau equal to tau naught R by capital R. Okay. Now just write in this particular equation, and for very close to the pipe wall, you can write tau equal to tau naught, and you can get the equation. You have get the equation for tau naught as this, and here for solving further, you can get the formula in this particular form, dv by dy. We need to formulate the equation for velocity only. Okay. Here This particular term tau naught by rho is actually shear velocity or friction velocity. Okay, you can write it as like V star or V asterisk, whatever you say. So just write equation for dv by dy, and by integrating this particular equation you will get this equation where c is your constant of integration. Here you can see the velocity distribution is actually logarithmic in nature. Just apply the boundary condition y equal to capital R, you will get its V max. Okay, get the value for c and put in this particular equation. Put value for kappa is 0.4, solve it further, you are going to get final velocity equation like in this particular form. So that is for all for today's lecture. We'll continue this particular topic in next lecture. Jai Hind everyone.